This video is about design. In the design process, we know the response that we want to get from the system. This defines the mathematical relationship between the input and the output of the system. Once we know that math relationship, we can implement a physical system that does that math. In a previous video, I talked about two ways that engineers use mathematical models. The first approach was model estimation, in which the mathematical model of the system was estimated from measured data. For linear models, we measured two data points and estimated the slope and the y-intercept from those data points. Our second way of using a model is to predict the system's response from the model and an expected input. A third way models get used is an alternate approach to model estimation. This consists of writing the theoretical fundamental equations governing the system components and their interactions and using those equations to generate a mathematical relationship between the input and the output. This approach has some pretty significant advantages, especially if you're designing a system. You can leave the governing equations as a function of some component parameter, such as, for example, the resistance of a resistor, the spring rate of a spring, or the wall thickness of a pressurized tank. Then, knowing the operating point of the system, you can choose values for these unknown parameters so that the system design requirements are met. So for the previous examples, you can choose a resistor that results in the desired current, or the wall thickness for your tank that handles the expected pressure. This process of using a mathematical relationship to choose appropriate physical components is fundamental to the design process. My design example is a temperature measurement system. The system needs to output a voltage that indicates temperature, and our design requirement specifies a desired sensitivity. The first requirement, a voltage output, means that our system needs to convert temperature to voltage. The reason we want a voltage is that engineers almost invariably represent data or information as voltage. This makes it easy for the system's output to be recorded or to be incorporated into other systems, such as a temperature control system. The second requirement, sensitivity, simply means that we have to have a minimum rate of change between voltage and temperature. So the system will need to produce a given voltage difference for each degree of temperature change. Our requirement is that the system produce a change of approximately 0.1 volts for every degree centigrade of temperature change. If we assume that the system response is linear, this specification defines the slope of the straight line. If I plot temperature on the horizontal axis and voltage on the vertical axis, the slope of the line will be 0.1. Our temperature measurement system will, like most engineering systems, consist of several subsystems that individually perform some simple task. Our first subsystem will be the thermistor I used as an example in a previous video. As we saw previously, a thermistor converts a temperature to a resistance. In order to have a linear model, the y-intercept of the line describing the model has to be 0. In a linear model, the relationship is a straight line that goes through the origin. In order to create a linear model, we choose an operating point and make that our new origin. So let's consider the temperature of the thermistor to consist of some operating temperature, T0, with some variation, delta T. The resistance will then be some resistance, R, that's the resistance at T0, with some change, delta R, that is caused by the change in temperature. We can choose the operating point arbitrarily. I'll choose the operating point to be room temperature, so R is the resistance at room temperature. Now we can consider the input to the system to be a change from room temperature, and the output is the corresponding change in resistance. Now the input-output relationship for the system is delta R is equal to some slope, m, times delta T. From the video where we used a frying pan to measure the thermistor response, the rate of change of R with temperature was found to be negative 220 ohms per degree centigrade. So this is the linear relationship that we'll use to characterize the transformation from temperature to resistance. Remember these two equations. We'll be using them later. The thermistor converts temperature to an electrical parameter, resistance. I can use a second subsystem to convert the resistance change to a voltage change. The circuit we'll use is called a Wheatstone Bridge. Adding the Wheatstone Bridge to the thermistor will result in a system that converts a temperature change, delta T, to a voltage change, delta V. The design of the bridge circuit depends on the operating point we chose for the thermistor. Now let's take a look at how to design the Wheatstone bridge. A Wheatstone bridge consists of 4 resistors, connected as shown here. The thermistor will be at this location in the bridge. The thermistor's resistance changes with temperature and consists of an operating point resistance, R, and a change in resistance, delta R, associated with a change in temperature from the operating point. The other resistances in the Wheatstone bridge are chosen to match the operating point resistance of the thermistor. The voltage Vs is an externally applied voltage that powers the circuit. It can be chosen arbitrarily. This circuit has a linear relationship between the change in resistance and the change in output voltage measured as shown here. Analysis of the circuit gives this relationship between delta R and delta V. The equation is the equation for a straight line that goes through the origin. It's delta V is equal to some number times delta R. The slope does depend upon the choice of our operating point resistance R. Our operating point is going to be room temperature. When we tested the thermistor, the room temperature resistance was measured to be 9,700 ohms, and if we arbitrarily use a supply voltage Vs of 5 volts, the equation becomes this, which simplifies to delta V is equal to negative 1.29 times 10 to the minus 4th volts per ohm times the change in resistance. Remember this equation because I'll use it later also. The circuit does provide the output in the form of a voltage, but unfortunately it doesn't provide the required sensitivity for the measurement system. We need one more subsystem to let us get the 0.1 volt per degree centigrade sensitivity that we need. We'll use a voltage amplifier as a final stage to adjust the overall sensitivity between a change of temperature and a change in output voltage. A voltage amplifier accepts a voltage as an input and outputs a voltage that's a scaled version of the input voltage. It just gives us an output voltage that's equal to the input voltage multiplied by some number. That makes it yet another linear system, and we can get the desired slope of the overall relationship by adjusting component values in the amplifier. Now let's look at a specific type of amplifier that'll work with the system we've designed so far. This circuit is called a difference amplifier. Its input is a voltage difference between these two terminals, and this voltage is its output. The output voltage is the input voltage difference multiplied by a number. That number is set by the resistances R1 and R2. There are 2 of each of these in the circuit. This is called an operational amplifier. It's a common component in circuits that perform mathematical operations. This equation governs the output voltage as a function of the voltage difference over here. It's the last piece of information we need to design our system. So our overall temperature measurement system design looks like this. A thermistor converts a temperature change into a resistance change. The Wheatstone bridge converts the resistance change to a voltage change, and the amplifier adjusts the voltage change level so that we get the desired 0.1 volts per degree centigrade sensitivity between the voltage and the temperature. Now let's replace these blocks with their mathematical representations that we determined earlier. So this resistance change, delta R, is equal to this number, negative 220 ohms per degree centigrade, times this temperature change. This voltage change here, which I'll call delta little v, is this number, minus 1.29 times 10 to the minus 4 volts per ohm, times this resistance change, which is minus 220 ohms per degree centigrade, times the temperature change. If I do this multiplication, delta V is equal to 0.028 volts per degree centigrade times the temperature change delta T. Finally, this voltage change, delta capital V, is equal to R2 over R1 times this voltage change, which is 0.028 volts per degree centigrade times delta T. Our required sensitivity between voltage and temperature change, delta V, is equal to 0.1 volts per degree centigrade times delta T. This number has to equal this number. So R2 over R1 times 0.028 is equal to 0.1. If I divide both sides by 0.028, R2 over R1 is equal to about 3.5. So that allows me to select resistance values that give me the desired sensitivity. It doesn't choose either of these individually. I can pick one of them arbitrarily. I'm going to pick R1 to be 2.2 kiloohms and R2 to be 6.8 kiloohms. That'll give me 3.4, which is probably close enough to my desired value. Now I'll wire up this system and see how it works. This is the circuit I'm going to use to convert the thermistor's resistance to a voltage. This section of the circuit is my Wheatstone Bridge. The thermistor's connected here and here. This is the operational amplifier, the op amp, and these four resistors form the difference amplifier. I'm using this DMM to measure the temperature of the frying pan. This DMM is measuring the voltage out of the amplifier. At room temperature, the output voltage is approximately 0. Let's warm up the frying pan. So we're going to go from about 24 degrees up to 34 degrees. Hopefully we'll get a 1 volt change in voltage. So when this is 34, that's 1 volt. This video provided a quick example of the design of linear systems. In the design process, the steps are usually as follows. We're given a set of design requirements that define the math that the overall system should perform. We develop mathematical relationships for candidate subsystems. These models will be functions of system component values. We can then choose the component values to implement the specified mathematical relationship. Notice that in our design we use linear models. That made the math really easy.